We see explosions all the time. And during my career as an engineer, I've certainly made a few. But actually understanding them and controlling all that power, that's a whole different story. And sometimes quite a surprising one. It's a story that starts with the accidents of the medieval alchemists.
Don't try this at home.
Whoa! But eventually leads us to a fundamental understanding of the forces of nature. Forces that we've mastered for good or evil. Explosives revolutionised battlefields, industry, and engineering. To uncover the story, I'll be reading the words of medieval scholars. Going deep underground through ancient Cornish mines.
That looks like a lot of gunpowder to me.
And making some of the most dangerous substances ever known.
It mustn't go above 18 degrees centigrade.
It's a journey that will take us right to the centre of matter. Is that a split atom?
Oh, yes.
Wow! And the power it can unleash. This is the story of how we learned to harness the forces that shook the world. The very first record we have of people using explosions comes from a Chinese document, which could date from as far back as 2 centuries BC. It describes how travellers in the mountain wilderness of the West were threatened by shape-shifting creatures of the night. To scare away these creatures, they would lay lengths of bamboo on their campfires. The very first Chinese firecrackers. The hissing noise we hear is moisture in the bamboo turning to steam. But bamboo has a special structure to it. It grows in sealed compartments. Now, when the moisture in these sealed compartments starts turning to steam, pressure builds up inside here. It can't go anywhere. Water, when it turns to steam, wants to expand hundreds of times, but there isn't room for it to do that, so pressure builds up. Eventually, the structure of the bamboo breaks down, it explodes, scaring away shape-shifting creatures of the night. Using simple, natural explosions like this was the first step of mankind's journey to harness explosive power, starting to understand the process in order to control it. It's easy enough to create an explosion. Any explosion is simply the moment when gas tries to expand suddenly. Oh! And when that suddenly expanding air crashed into the air around it, it created a pressure wave that then moves through the surroundings. The sudden change in pressure forced a cloud of water droplets out of the air. These allow us to see the wave. The faster the gas is trying to expand, the more powerful the explosion. And when that pressure wave hits your ear, you hear it as a bang. An explosion relies on a lot of gas trying to expand. Heat can make this happen, because heat, of course, makes things expand. Introducing more gas can do the same thing. But mankind discovered a way to create both heat and gas by reacting chemicals together. And this was the start of our journey to really master explosive power. In Europe, chemical explosions were unknown until the medieval period. And the first time people came across them, they were a bit shocked. I've come to the Bodleian Library in Oxford to see a manuscript that describes one of these early encounters. It's one of the few copies of a book written in 1267 by the medieval scholar
Roger Bacon, who split his time between Oxford and Paris universities.
Now, this particular passage that starts et experimentum describes his knowledge of man-made explosives at the time.
There is a children's toy, something no bigger than one's thumb, made in many parts of the world, that is an example of how something can assault the senses with sound and fire. It is no more than a bit of parchment, which contains a powder combining the violence of that salt, called saltpeter, together with sulphur and willow charcoal. But the bursting of this small thing assaults the ear with a noise that exceeds the roar of thunder, and a flash brighter than the most brilliant lightning.
Now, I suspect he may have been exaggerating slightly, but this was the first time that anyone in Europe had come across man-made explosives. Now, Roger Bacon was a Franciscan friar, and the church at that time had envoys all over the world. It seems likely that one of those envoys must have posted a package back to him containing these children's toys. The big question is, though, where exactly did that package come from?
In the Middle Ages, the most technologically advanced region of the world was China. A printed book dating from before the Battle of Hastings indicates that the Chinese were already deploying explosives of a similar sort on the battlefield.
What we have here is a Chinese military manual, first printed in 1044, and in it we find a recipe for a thing called the fire mixture, or the fire chemical, which contains the principal 3 ingredients in Roger Bacon's recipe of 200 years later. We start off with, here we have these 2 things here. They're both forms of what we now call sulphur.
Right.
Followed by various forms of organic matter like pounded dried roots and twigs that produce the carbon. Followed by saltpeter, the next one, yenxiao. The saltpeter is something you get from the decay of organic matter in relatively warm conditions. The Arabs referred to it as Chinese snow.
Right. So China was just a good place at the time, like it had the right climate for saltpeter to occur like that.
Mm-hmm. There's a lot of things that come together, but certainly the availability of the right climate to get it is certainly important.
Can I start assembling it in the right proportions?
Certainly. Well, roughly you want to put in about 50% of our saltpeter.
For every, what, one of those or
Yeah,
something?
that's equal amounts of the powdered sulphur that we've got and the powdered charcoal.
What were they trying to make at this point?
This is a mixture for parceling up and throwing basically into an enemy city using a catapult like this. This thing here is called
really?
a horpao, which means a fire catapult.
Now, from my knowledge of chemistry, saltpeter is what they call potassium nitrate.
That's
nowadays,
right.
Yeah. And that's got kind of oxygen bound up with
That's
nitrogen
right.
inside it.
If we warm it up, it'll let the oxygen loose, and then that will aid the burning of the other ingredients. The sulphur basically helps everything to happen at a rather lower temperature before, and ultimately, of course, the carbon is the main source of the stuff that burns. Well, there we go, that's good.
Look at that!
Take the flame away now, see it go in its own. That's
Oh.
very nice.
That's fabulous!
I'd call that an effective incendiary, wouldn't you?
Yeah, I can imagine once you get a bucket load of that landing in your camp.
It's discouraging, isn't it? It makes you wish you hadn't come.
Yes.
The black powder that the Chinese military were using in 1044 had got grains of different chemicals close enough to react together and produce lots of heat and gases. In the open air, there's plenty of room for the gases to expand, so there was no sudden explosion, but the basic chemistry of gunpowder was there. However, an even older Chinese book suggests that the very first chemical explosive in the world had been developed 200 years before this.
A book with the lovely title, Classified Essentials of the Mysterious Way of the Origin of All Things, which happens to contain a few recipes listed as, don't try this at home if you are an alchemist. And amongst that is a recipe which I think we ought to try.
I'm game.
You have some saltpeter, you have some sulphur, those 2 ingredients. The carbon comes in the form of honey.
OK. And what kind of quantities do you reckon they use?
I would say most of that jar would get us something interesting happening if we got about the same quantity of the other 2 ingredients, the saltpeter and the sulphur, that should go nicely.
Why did they ever think of mixing these things together at this point?
The idea is to try to subdue the fiery properties of the sulphur and of the saltpeter so that they will be suitable for taking as a medicine, hopefully an elixir of life.
Oh, I see.
So, ironically, in trying to find a means to eternal life, the Chinese alchemists found a substance that could kill.
I've never done any alchemy before. This is my first venture into the world of alchemy.
If you make a success of it, it's a new career, really, isn't it?
Potentially lucrative, I think.
Yes, indeed, indeed. Now, that looks pretty well stirred to me. I would think now if you start cooking that, that will finish the mixing.
Despite being earlier than the incendiary powder of 1044, the chemistry of this mixture has the potential to be more explosive.
So, because of the water in the honey, that is dissolving the saltpeter,
Yes.
and then allowing that to carefully coat all the bits of
All the
sulphur.
particles of carbon and sulphur will now be very, very close to molecules of saltpeter, which, when they get hot enough, will start releasing their oxygen just right up close to them.
I think that's going to go in a sec.
There's little puffs there, exciting little puffs, I say. We slightly move ourselves out of the immediate line of that, that's it.
Whoa! Okay. Wow.
That was quite striking.
Wow.
Yes. Well, as the Chinese alchemist said, don't try this at home.
So, incendiary mixtures were being explored by the Chinese alchemists as early as the mid-9th century. From the 12th century, as China was swept by waves of war with neighbouring peoples, they started to use their fast-burning powder in a new way. No longer just an incendiary, it became an explosive propellant for projectiles. The Chinese gave their new weapons names like the fast-as-heaven enemy-exterminating yin-yang shovel, the scary, ingenious, mobile, ever-victorious poison fire rack, and my personal favourite, the orifices-penetrating flying sand magic mist tube. In all of them, they put the powder in a tightly confined space, and this fundamentally altered the way it behaved. It was the discovery that would change warfare forever.
Confining gunpowder changes the speed of the reaction. It goes from something that just burns into something that really explodes. Gunpowder doesn't need air in order to burn. It gets all the oxygen required from the crystals of saltpeter, potassium nitrate, that are in there, which means it'll still burn in a confined space. And putting it in a confined space increases the rate of reaction. Drop it in here. So I'm going to wrap it up. When it's confined like this, all those grains, the carbon, the sulphur and the potassium nitrate, are all physically much closer together, which means the reaction can happen more quickly. And as the reaction happens more quickly, more heat's created, making the reaction go even faster, and it's a runaway process. Right.
With gas being produced so quickly and heat making it expand, there's the potential for explosive force, if I can channel it like the Chinese did.
This is my first attempt at a cannon. I've decided to build it out of clear acrylic so that we get to see what happens inside a cannon. Now, I'll drop that on there. Oh, it fits in nicely. My cannonball. So there it is. There's going to be an explosion in there. That explosion will produce hot, expanding gas. There will be a big pressure rise in that part of the chamber. That pressure will exert a force all around the container, but these three sides should stay where they are. This fourth side here, where the tennis ball is, won't stay where it is, and that tennis ball will leave at an undetermined speed that I suspect will be pretty quick. Let's find out. Yeah, that worked like a cannon should work. Wow.
You can see how the gunpowder produces hot gases at just the right rate to push the ball out. This technology quickly spread west, through the Middle East, and by the 14th century, the Europeans had rockets and guns too. But something else was happening. Gunpowder was spreading beyond the battlefield. Its power was being put to work in mines and engineering projects as Europe became more industrialised and there was demand for more powerful and destructive explosions. Gunpowder had reigned for 500 years, but now its dominance was about to be challenged.
The middle of the 19th century provided a turning point in the story of explosives. I've had to come here to the Defence Academy of the UK because we're going to make what they first discovered in 1846.
There was a growing tradition of pure scientific research in Europe, with researchers trying to understand the chemical composition of natural substances. One of these chemists was a German from a humble background called Christian Schönbein. He was naive, unconventional, and full of original ideas. Working in Switzerland, he'd seen some unusual reactions with concentrated acids and was keen to investigate them further. One of those investigations was unwittingly to change the world of explosives forever. Professor Jackie Akhavan has volunteered to show us exactly what Schönbein did.
Jackie, what are we actually doing here?
Okay, we're mixing nitric acid and sulfuric acid together, and then we're going to add some cotton wool to it to hopefully nitrate the cotton wool.
Schönbein didn't know it, but the cotton will be acting as a source of carbon, like the charcoal in gunpowder. And by nitrating it, he added oxygen and nitrogen from the acid actually into the molecules of the cotton, rather than just being in neighbouring grains.
We must make sure that the temperature remains cool. So I'm going to put a thermometer in so we can measure the temperature. Do you want to help?
I do. What temperature should I watch out for?
Okay, it mustn't go above 18 degrees centigrade.
Okay.
So I'm going to adjust this one. Did you give me an update?
It's at 21 at the moment.
Right.
I don't want to scare anyone.
No, it's okay. Okay, what we do, we just cool it down a bit. Okay. So what temperature are we now?
It's down to 19.
Okay, well, we need to get a bit cooler.
We're down to 18.4.
Okay.
So what's the danger if the temperature starts rising?
We just want to keep control with this reaction.
I'm very conscious of this.
That's okay. No, it's,
I know battery acid's quite horrifically dangerous, and if that's just as dangerous...
It's much... These are very, very concentrated acids, so we've got to be extremely careful.
The nitration reaction changes the cotton chemically, so that now, just like in the gunpowder mix, there are carbon, nitrogen and oxygen atoms, an explosive reaction waiting to happen. But in this substance, they are actually all in the same molecule, so much closer together than in gunpowder. Schönbein had accidentally created a much more efficient explosive.
So this is it, our nitrocellulose, or gun cotton, as it's known. I mean, now we've washed the acid off and dried it, it feels exactly like cotton wool, just like we started with.
The only difference with this one compared to the cotton wool is that we've got the oxygen actually linked to the fuel.
So because we've changed every single molecule of the cotton to gun cotton, then it's going to go exactly the same every time.
Yes.
Go on then.
Right, are you ready?
I'm more than a little intrigued.
Okay. Stand back.
I am already.
Ready?
Ooh. That gives off a lot of heat.
Heat, light, lots of gas being given out, and then you can just have a look, and there's sort of black bits there, that's the carbon, so it hasn't fully oxidised.
Right, so there's not enough oxygen for all the carbon that's in the molecule, so we're just left with some carbon.
That's right.
And that's just a very, very rapid burn, that woof. Like with the gunpowder, when you just set it fire, it's unconfined, so you don't get an explosion, you just get this rapid burning.
It all goes up into the atmosphere, and it's all disappeared as gases, and, you know, that's what you're left with.
I like it. Can we do some more?
You can indeed.
Just like gunpowder, gun cotton simply burns when there's room for the gases it produces to expand into. But it burns faster, and the faster the gases are produced, the greater the explosive potential. Schönbein recognised it, and immediately started sending out samples to colleagues and writing about his discovery. One of the first to react to the news was the Cornish mining community in the far southwest of England. The area is rich in resources, like tin and granite, and it made it a worldwide centre for mining. It was a vital and profitable industry for England, and in the mid-19th century, it relied heavily on gunpowder to break up the rock.
By the 1840s, miners had been using gunpowder in mines like this for 200 years.
But gunpowder was far from reliable. It was dangerous, unpredictable, and difficult to use. Mine historian Richard Williams has promised to show me just how difficult, starting with how they got it deep within the rock.
We were trying to actually push a hole into the rock using what they call a bore, a basic iron bar, usually about 3 feet long.
Right.
And a heavy hammer. Would you like
Can I have a go? I'd
Yeah.
love to have a go.
Keep turning it.
I can see that taking a while.
It would probably take you a good 20 minutes.
I can imagine once you've done your 3-foot hole, you'd want to get the best bang out of it you could.
Oh, yes. Well, the next thing is to charge it, to fill it with gunpowder.
And you can imagine if they're working with candles or open lamps and gunpowder, it's not a great combination. Okay, so once they've got the gunpowder into the hole there, how do they safely light it?
They used goose quill. Basically, the centre of the quill is hollow.
Yeah.
So you cut off the top, you'll end up with something like that. You grind your gunpowder up until it's fine enough to go into the hollow.
Yeah.
Tamp that down. Make several of those, push one into another, and slowly you make a fuse.
And they're all packed with gunpowder, so I can see, but what was the burn time on them? Like, how quick did they go?
They were unpredictable. If you didn't actually pack them correctly, they would go off a little bit like a rocket.
That's horrendous.
Well, when we're doing it, we're actually going to use safety fuse. And we've already made a charge up, and basically we filled this with gunpowder, and we've already got a hole drilled. The hole is going back into the rock.
Okay.
So we put their powder into the hole. They would then get a tamping rod to push it in. Next thing is to stem it, to seal it.
Right.
Because if we left it like that, it would shoot just like a gun.
Yeah. Visually, this looks quite a short fuse to me. How much time have we got from when we light it?
This is going to take about a minute and a half, slightly over a minute and a half to burn through to the gunpowder.
That still seems quite quick, but I'll trust you. I'm going to wear my goggles, though.
Away it goes.
Oh, yeah, look at that. I say look at that. Should we not be moving in that direction quite quickly?
I think we should leave now, yes.
Yeah. So we can just literally just pop round the corner here.
Get the corner out of the way, so we're out of the way anything that flies down through the tunnel. You start to wonder if it's going to go. But it went.
You feel like the
you feel the shockwave
reverberation
coming,
afterwards
yeah.
as well, which I guess is the multiple shockwaves bouncing off all sorts of walls. Whoa.
But there we go, and you look down the level and we should see the smoke. Now you can actually see the fumes are close to the roof here, looking down through.
Oh, yeah.
So it's getting thicker as we get close to the...
It's getting a bit acrid, isn't it?
The smoke was one of the things that miners hated about gunpowder. It filled the tunnels and made working difficult.
And what's actually happened
Is
blown the stemming out.
we haven't moved any rock at all, have we?
No.
So not only was gunpowder difficult and time-consuming for miners to use, it wasn't even that reliable. Schoenbein's new gun cotton promised more power, more reliability, and no smoke. In August 1846, the Royal Geological Society of Cornwall invited him to come to England to prove its worth. Schoenbein demonstrated his gun cotton in a quarry like this. The quarrymen drilled several holes in the rock, and into one they packed a full charge of gunpowder, and into another, just a quarter of the amount of gun cotton. So innocent did the gun cotton look that one man said he would sit on the hole
in return for a drink at the local pub. Luckily, he was persuaded to watch the test before committing himself to the bargain.
First, 30 grams of gunpowder. Let's see if it's more successful than in the mine.
Well, the rock split, but not at the hole where the explosives were. It looks like that explosion there maybe sent some kind of shock through the rock, and it's peeled off here where possibly there was some sort of fault line.
Now we'll try just 5 grams of gun cotton, looking like it couldn't possibly do much damage.
That's a completely different story.
In slow motion, you can clearly see all the gases the explosion creates. Brown nitric oxide, steam and others splitting the rock apart.
It's just astonishing. A couple of 100 kilos of rock has practically disappeared. There's some fragments over there, bits down here, and look at that. Where it was actually placed, there's nothing at all. Like that. Look down here. That's the hole where it's packed in. So this was the other way up. You can see where the clay was. You can see all the way down here, and it's just split it. Now, this is gun cotton, and what's happened here is when the gun cotton has been compacted, confined in there, it's detonated, which is a completely different process to when we saw it being lit. It burnt rapidly. This detonation sends out a sharp shockwave, and as it goes into the rock gets split. It's a much more powerful explosion, and I can imagine the Cornish miners feeling a little bit like me now, almost overwhelmed at the difference between gunpowder and gun cotton.
The quarrymen were amazed at the new gun cotton and mercilessly teased the colleague who had offered to sit on it. They were immediately interested, and Schoenbein quickly found an English partner to start manufacture. His apparent success soon inspired others.
Schoenbein wasn't the only one experimenting with these kind of chemicals. Not long afterwards, an Italian chemist, Ascanio Sobrero, reacted nitric acid with glycerine, another carbon-rich substance.
Sobrero had worked on nitration before, and when he read of Schoenbein's discovery, he was inspired to return to it. He was originally a medic, so many of his interests were in potential new drugs. The result of this experiment, first done in 1846, is in fact still an important heart medicine, but it has another side to its character. Dr. Alex Contini is one of the few chemists experienced enough to attempt this process, and he isn't going to trust his life to me keeping an eye on the thermometer this time.
7 and rising.
Each time the glycerine is added to the concentrated acids, he has to stir it and make sure it stays cool. Every degree of temperature rise makes a premature explosion more likely.
10 and rising.
The resulting oily liquid, like gun cotton, contains carbon atoms linked to nitrogen and oxygen groups. It looks fairly innocuous, but Sobrero discovered it has some pretty surprising properties.
And we're only going to use the tiniest amount to show them.
Sobrero wrote that the safest way to demonstrate these properties was to dip a hot wire into a glass bowl of the substance. But he was scarred for life by flying glass, so we are going to try something different. If you look down there, you'll see the nitroglycerine has completely disappeared. Every molecule of the liquid nitroglycerine gets turned to gas and goes, hence the massive expansion, hence the massive explosion.
Whilst gun cotton only detonates when confined, nitroglycerine can detonate when given a simple sharp shock. Even slowed down, more than 500 times, the explosion is incredibly fast. This new behaviour made gun cotton and nitroglycerine quite different from gunpowder.
The difference between gunpowder and these new high explosives, as they're called, is the way they explode. Gunpowder burns, albeit very rapidly. It's still burning. One piece heating the piece adjacent to it, the piece adjacent to that, until the whole thing's gone. With high explosives, it's detonation. A pressure wave travels extremely quickly through the whole charge, and it almost goes instantaneously.
The first bit of the reaction in a high explosive creates so much gas so quickly it generates a pressure wave that hits the rest of the explosive. I'll show you with this fire piston, as it's called, and a tiny bit of normal cotton wool. As the piston comes down, it acts like the explosive pressure wave, raising the pressure inside the tube. That pressure heats the air so much that the cotton wool bursts into flame.
It's the same with a piece of high explosive. It's the sudden rise in pressure that gives the sudden rise in temperature that triggers the explosive as it runs through the entire charge. Now, this thing happens so quickly, you pretty much get the entire lot going in one go.
Watch this.
This is detonating cord. It's a spun cord with a line of high explosive right down the centre of it. When it's detonated at one end, the wavefront moves extremely quickly right down its length.
Slowing the process down 250 times, you can see the detonation travelling at about 6 kilometres a second. When the force of the detonation wave hits the surrounding air, it creates a supersonic shock wave. You can see the shock wave distort the air like a bubble coming out around this modern high explosive.
Shock waves and reaction speeds like this were a phenomenon that nobody had come across before, and it made these new high explosives very powerful and potentially very dangerous.
And that was the problem. Only months after it opened, the world's first gun cotton factory exploded disastrously in England. And Sobrero's new nitroglycerine appeared even more dangerous. It seemed there might be no way of safely harnessing this newfound power. But the industrialised world was crying out for it. The men working the great tin and coal mines of Britain were still having to use the centuries-old, inefficient gunpowder. And attempts to build a canal system to move the vital raw materials produced by the mines to Britain's ports were hampered by gunpowder's lack of power. But in the 1850s, a young Swedish student came to hear about nitroglycerine. His name was Alfred Nobel, and his family were explosives manufacturers in need of money. They took the risk of trying to manufacture nitroglycerine, but they had an awful lot to learn.
In their first year of manufacture, their factory in Sweden exploded, killing Alfred's younger brother, Emil. This is the site of Nobel's biggest explosives factory. It's at Ardere on the west coast of Scotland, and at its height, it was the biggest explosives factory in Europe. Nobel liked it. One, because it was remote, but two, it was built entirely on sand, meaning he could create artificial landscapes like that. Nobel built what were called nitroglycerine hills. Nitroglycerine was made in little huts on the top of each hill. In each hut were two men, one to monitor the mixing reaction, the other to adjust the flow of water through a cooling jacket to keep the temperature in the right range. Now, vigilance was vital. The entire batch could self-detonate if allowed to go out of control. For this reason, one man had to always sit on a one-legged stool, so there was no chance of him falling asleep on the job. I mean, as if sitting next to a vat of nitroglycerine was not stimulation enough. Nitroglycerine could not be safely pumped. So what they did was just let it flow under gravity from the huts at the top of the hill to the factories at the bottom. Once inside the factory, it got stabilised. Now this was what was Nobel's great achievement. He discovered that if he mixed his nitroglycerine with an absorbent clay, a bit like cat litter, it became a lot less sensitive, a lot easier to handle without going off in your hands. The clay he used came as a fine powder called kieselguhr. Once mixed together, a dough-like substance was formed. In fact, it was kneaded by armies of women into the shapes required. This new compound was called dynamite, and it was a revolution. Now, there was a high explosive that was insensitive to shock and heating. You could actually set fire to it and it would burn with a normal flame. I don't recommend it, but apparently you could. But once you've made something that's this good, that's this stable, this difficult to set off, how do you get it to explode when you want it to? That was Nobel's other great innovation.
And they actually still make those devices at his old factory. In fact, Nobel's sand bunkers are the perfect place for me to find out more about them.
Well, Alfred Nobel, being the very inventive guy that he was, came up with the idea of a detonator. And this is a modern detonator, but the basic principle is a device which delivers an explosive shock to dynamite, and that shock is sufficient to detonate it. I do actually have a cutaway here. At the top of the detonator we have an electrical fuse head, and this is in many ways like the match.
Yeah.
This is designed to initiate not by friction, but by passing an electric current through it.
Yeah.
That generates heat, which causes this fuse head to burst with hot gases and hot particles, which then initiate a pellet of sensitive primary explosive.
And out of more than just casual curiosity, a detonator like that with that much explosive in it, how much damage would it do if just that went off?
If I was holding this in my hand and it were to detonate, then I would lose the hand.
Really? Okay. I will be very wary of detonators then.
Absolutely.
Of course, to demonstrate a detonator really doing its job, we need to attach it to a block of less sensitive explosive. Dynamite was the world's first mouldable plastic explosive, and we're using its modern equivalent.
That's a small sample, maybe about 30 grams of our new plastic explosive that we've developed here at Ardea.
I mean, I should double check. I'm fine for handling this now.
Oh yeah, it is perfectly safe.
I guess because it looks like Play-Doh, you instantly want to treat it like Play-Doh.
Well, it is a very special kind of Play-Doh, if you like. It's got that plasticity that Play-Doh has, but as with all explosives, they are very, very unforgiving when you give it the right stimulus.
And that is a detonator.
And that is a detonator. If I could ask Jim to come in and set up. Jim is one of our trained shot firers, and only a shot firer can set up. You've been handling that material with gloves. Jim is not wearing gloves because there is a risk of static with the electrically initiated detonator. You'll notice again that he's kept the detonator, the action end of the wires, in the box until the last minute, so if there is any accidental stray current, he's minimized the chance of it causing any damage. And then he just simply pops it into the holder to make sure that there's contact with the explosive, and it's now ready to go. Once we've cleared the site, and Jim has armed the circuit.
I feel my stomach change when he puts that in there. Like, I honestly do. It's just... like, we're now... Shall we go?
Yes.
Right.
Okay.
Stand by. Effectively, that entire lump almost instantaneously goes from being a solid to a gas.
Absolutely right.
It's shockingly crisp.
Yeah, and that's what it's supposed to do. But if you look on the other side, you'll see something completely different.
So, and that's the pressure wave that's ripped that out.
Yeah, the shock wave travels through the plate, hits the underside, and then just blasts off the scab. And if we dig around, we might just
Find the back end of that.
The back end of that, because we've got a nice little hole here, so somewhere down there
Should be the piece of metal that's missing.
Well, the secret is it's come all the way through. And there,
I'm
get the sand off it,
shocked.
is the scab that's come off the other side.
See, that's almost more impressive than going through there, because nothing goes through railway sleepers, as a general rule.
Nobel's struggle to tame the power of high explosives and make them safe tools for the hungry industrial world made him a very rich man. By safely harnessing the shattering power of nitroglycerine's detonation with dynamite and a range of other compounds, a new era of civil engineering opened up, and great construction projects such as the Suez Canal, the London Underground system, and then the Panama Canal could now be undertaken.
And that might have been Nobel's legacy if it weren't for a mistake that occurred in 1888. After the death of Alfred Nobel's elder brother Ludwig, some newspapers mistakenly printed Alfred Nobel's obituary instead. Now, where he was living in France at the time, Le Figaro printed this small but damning paragraph. It translates as, "A man who it would be difficult to describe as a benefactor to humanity died yesterday in Cannes." Now, reading that must have been a bit of a shock, and it said that it made Nobel intent on changing his legacy to the world. To that end, he left his vast fortune to setting up a foundation which would award prizes for literature, science, and peace.
Nobel's advances in explosive design were the result of long hours and hard work. But some revolutions in the history of explosives are sparked simply by a chance observation.
In the same year that Alfred Nobel's obituary was accidentally published, an American chemist, Charles Monroe, was doing some explosives work for the US Navy.
He was one of the foremost explosive experts of the late 19th century. Then, many high explosives came in blocks with the manufacturer's name embossed onto them.
So I've got myself some high explosive, onto which I'm going to stamp a corporate name. Now, as Monroe spotted, there was something very strange that happened when these stamped blocks were detonated near steel plate. Hopefully, we'll get to see the same thing. Fine. That seemed big enough. There we go. Yes. Okay. You can now see the BBC logo stamped into a block of steel, in the same way that the manufacturer's logos got stamped into the steel back in the 1880s. But what Monroe was particularly intrigued by was why it made this particular indentation from the indentation on the explosives. And understanding the way in which this happens led to a completely new way of using explosives. When a lump of explosive detonates, the shockwave radiates out from every part of its surface. So, if you've got your dent in the explosive here, and you've got your target there, what happens is, as the shockwave comes out, instead of the bit at the back ending up with a weaker effect, it ends up actually stronger, because the shockwave is coming out in all directions like this. When it reaches the centre of the indentation, they tend to meet like jets of water in the middle of that dent. And this effect here magnifies the shockwave that you've got leaving there, sending it into the plate, and this is actually the area of maximum pressure here. And once this was understood, shockwaves could be directed to focus the power of the explosion exactly where it was wanted.
People started making cavities in their explosive to increase the power of the shockwave. But then, with the pressures of war, came a new step forward.
When you line that cavity with a hard material, almost invariably metal, then you enter the domain of what's known as the shaped charge.
Right.
Conventional shaped charges are filled with high explosive in a factory.
Right.
This is something that I designed for filling by the user. It means that it can travel on aeroplanes and so on without
DIY
friction.
shaped charges.
Exactly that. Now, in this case, we're going to go back to probably the first type of liner. This is called the liner that was used in a shaped charge.
That's just a cone of copper, isn't it?
It is indeed.
And then having that copper on there, I guess it's the sort of the equivalent of using a bullet or a cannonball. So it's saying that, you know, if you go and just fire an empty kind of cartridge, then you get a loud bang and an explosion, but nothing that's going to do any significant harm. Whereas if you put like a bullet in the end of it, if you see what I mean, and fire it, then it pushes out something of a significant mass, and that can do some damage.
Yes. The great advantage is that this metal travels enormously faster than any cannonball. I'll show you what I mean. If you put plastic explosive in here, and then you push this copper cone into the explosive, when I initiate at this end, a detonation wave travels from here to there.
Right.
First thing it hits is the apex of the cone. And that apex of the cone is driven forward. The whole cone is collapsed. In fact, it collapses in such a way that it turns inside out.
Right, because the end bits hit first and that starts moving. Wow, that's an astonishing thing to get your head round, though.
It is a bit of a shock at first. What happens is that the inner part of the copper, not the whole mass of it by any means, the inner part of the copper forms into a sort of wire, which is called the jet.
And that's not molten, it's still solid copper.
Yes, but coming not in that direction, coming that direction.
Of course, yes.
It's counterintuitive.
And then that almost like piles in like a nail through the steel, driving its way in.
Yes, it pushes the target material out of the way. And it pushes it aside as the tip of the jet hits the steel and flows back along the outside of the rod. Then there's a new increment of metal. It is constantly being replaced. And when it's all used up, stops, won't go any deeper.
Are we in any kind of position that we can try this and I can see?
Absolutely. This box, I'm pleased to tell you, is full of explosive.
Good.
What I'll do is take some out. This is standard British plastic explosive. It's similar to the American C4, but it is actually much easier to use for filling charges. You can just ram it in and then put the cone in.
We're going to test it with what looks like an impossibly solid block of steel. There is a critical distance at which the jet will be at its most penetrating before it breaks up, so the charge has legs to hold it the right height from our target.
Right. See you in about 2 minutes.
Yes, and don't panic.
I won't. Firing. 4, 3, 2, 1. Wow.
Go and see what we've done, Troy.
It seems astonishing because that's such a massive thump that something extremely accurate will have occurred from that.
Well, let's see.
Ooh.
Well, it's gone in at least that deep because I can push that in. But then the proof of the pudding will be turning it over and see if we have achieved anything the other end. Yep.
Oh, yes. But that's gone through over a foot of steel. The thing that I find it even more surprising is, you know full well, if you've got a copper nail like that, no matter how hard you hit it, it's not even going to hardly dent the steel. Exactly. Yet, you know, you get a good amount of plastic explosives with a nice shape behind it, and you can drive it the whole way through.
These cone-shaped charges allowed people to get much more focused power from their explosives, and during the coming world wars, revolutionised the power of handheld weapons, such as the bazooka. Nowadays, they're used in all sorts of military and civil applications, such as opening up oil wells, and Sydney designs them especially for bomb disposal. But other shapes have been developed as well for different tasks. This long, L-shaped liner can turn the shockwave into a blade, as the sides are slammed together. Instead of the cone's penetrating jet, this cutting blade is axe-like, designed for demolition jobs.
4, 3, 2, 1.
It seemed as if the power of explosives had reached a maximum. The chemical compositions were carefully designed, and the power of the shockwave could now be channeled. But there was still explosive potential beyond imagination to be realised. By the end of the 19th century, chemists were discovering new elements all the time, and some of them appeared to give off energy. They called this rather bizarre property radioactivity.
It was a New Zealand physicist, Ernest Rutherford, who was one of the first to understand the potential of radioactivity. Already understanding that it was caused by the atoms of the elements breaking down, he wrote this in 1904. If it should ever be found possible to control at will the rate of disintegration of the radio elements, an enormous amount of energy could be obtained from a small amount of matter. It was a prophetic statement, although he later said, anyone who expects a useful power source from the transformation of these atoms is talking moonshine. Even a genius doesn't get it right every time.
The investigation of radioactivity and the nucleus of atoms continued as researchers sought to understand the minute structure of the world around us. But some people were already seeing the potential for extracting the power released when nuclei are broken apart. And in the winter of 1938, with war already brewing, the exact dimensions of that potential was made clear in a laboratory in Copenhagen.
An experimental physicist, Otto Frisch, who'd escaped Hitler's regime in Germany, constructed a piece of apparatus to measure the energy released when an atom splits. Now, it's not my field of science, but he knocked his up in a weekend and did the measurements, so I feel there's a fighting chance for an amateur like me. All the apparatus really consists of is a metal box with a metal plate in it. Now, when an atom splits, you end up with two high-energy fission products. Now, as they fly through the gas around them, they can smash electrons off other atoms, causing ionization, producing positive and negative particles.
The atoms that Frisch split were of the element uranium, and he did it by bombarding them with particles called neutrons.
A couple of 100 volts between here and here should enable us to detect if there's been any ionization in here, and from that we'll be able to deduce the energy released when an atom splits. Obviously now all I need is a source of uranium and some neutrons to bombard it with.
The National Physical Laboratory near London had the sort of thing I need, so I've bought my part of the kit.
That is your ion chamber, is it?
Well, yes, this is my ion chamber.
Right, yeah.
It's not at the top end of the sophistication that you've got here,
Right.
but can we try it?
Well, by all means. I've got a piece of uranium here which I borrowed from our radioactivity group.
That's not a phrase you hear a lot.
No.
Uranium does have a reputation. How safe is it? How long can I be near it?
Provided you stay a few centimetres away from it, you are out of the range of the alpha particles.
Right. So I'll put the lid on here. The thing that we're missing, though, is the thing to split the atoms.
You need a neutron source.
Yes.
Right. We are the neutron standards laboratory for the UK. And we produce neutrons and use them to calibrate personal dose meters, like the ones we gave you to wear.
Yeah, I've got mine.
And I can get a neutron source, but you will have to leave while I put it up here.
OK, I'm happy to get out of the way while that's happening.
Right, OK.
The neutron source contains an element whose radioactivity is much more penetrating than uranium's, so it has to be treated with care.
OK, so we've now got our uranium being blasted with neutrons.
Yeah.
How do we tell if we're splitting any atoms?
We'd have to see some pulses from our ion chamber.
OK.
So if I turn up the volts, we might begin to see something. And the first thing we might see, if it works, is the natural radiation from the uranium. I am rather astounded, but they look like genuine pulses.
So this would be what you'd hear on a Geiger counter going...
Yes.
Right.
Yes, but of course you're not seeing any fission yet.
Oh, we're not?
Well, if it was fission, you would see some very much bigger pulses. So if I turn the discriminator up...
That is a massive pulse. Is that a split atom?
Yes.
Wow.
considerably bigger than the pulses from the natural decay of the uranium.
This is a completely different thing.
Yes, very much more energetic.
Now, from this, can we get a measure of how much energy is being produced every time an atom splits?
Well, the classical figure is 200 MeV, 200 mega electron volts.
That makes that, the energy released when one of those atoms gets split, is about 15 million times more than a molecule of nitroglycerine.
Yeah.
That's... You can see they're onto something.
They were indeed.
Frisch finished his weekend's work in the early hours of January the 13th, 1939, and was soon woken by a telegram with news that his Jewish father had been released from concentration camp. He said he remembered it as his lucky day, but would have liked a few more hours' sleep. As war rumbled across Europe and then the world, physicists in many countries grasped the potential of Frisch's experiment. In the early morning of the 16th of July 1945, a team of international researchers became the first to see that potential realised in the deserts of New Mexico. Inside a giant sphere of shaped charges, like the one Sydney showed me, they placed radioactive material, no bigger than an orange. The whole contraption was hoisted up a tower, and then the charges detonated. The initial flash of light and heat travelled out at 200,000 kilometres a second, with temperatures reaching over 100 million degrees, 20,000 times hotter than the surface of the sun. It melted the sand in the desert. Just like other explosions, this heat causes a massive expansion in the surrounding air. There's no production of gas like in a chemical reaction. It's simply the staggering quantity of heat released by a runaway nuclear reaction that causes mankind's biggest explosion. That expanding air slams into the air around it, causing an abrupt shockwave, which crushes the air, and just like in the fire piston, heats it, but to such a temperature that the air itself begins to glow. You can see the white-hot bubble-like shockwave in these astonishing pictures. Then it cools to a dark, transparent layer, and the fireball inside shows through. The Trinity explosion, as it's known, had the equivalent power of 20,000 tons of TNT, all from just a few kilos of radioactive material. And all that power and that enormous shockwave is produced just simply by heating the air. In some ways, it's similar to the heat causing the bamboo to burst back in ancient China. But with a nuclear explosion, the heat is almost unimaginably intense and sudden. In little more than 2,000 years, the journey of understanding that mankind has so far travelled is immense. We've gone from crackling bamboo to creating something like a star here on Earth. And man-made explosions terrify us as much now as they always have. The advent of the nuclear age was as shocking to us as gunpowder was to medieval Europe. Throughout history, explosives have been used first as weapons and then had their power harnessed to more constructive ends. They have shaped our world through warfare and engineering. Even nuclear power has been turned to peaceful uses. New explosives may always be discovered and wreak terrifying havoc. But if history has taught us anything, it's that by properly understanding these things, we can create instruments of unrivaled power. If you want to find out more about the science of explosions, go to the website bbc.co.uk/bang and follow the links to the Open University.
She may have been executed by Elizabeth I, but it was Mary Queen of Scots who put a child on the throne. Simon Sharma's History of Britain continues here on BBC4 Next. And then how the very air around us is made up of things that are vital for survival. Every breath we take at 10.